In the stillness after the first fire, when the newborn universe had only just cooled from its violent birth, silence stretched across an ocean of darkness. For hundreds of millions of years, the cosmos waited an empty stage of hydrogen and helium, a void without form, without light. Then, one by one, giants emerged. The first stars, vast, searing titans, far larger than any that would follow. They burned with ferocity, fusing the first elements, illuminating the abyss with a light never before seen. But their brilliance was brief. Their lives ended almost as soon as they began. When they died, they did not fade gently. They collapsed. Their cores imploded, crushing matter into a point beyond comprehension. Space itself folded inward. Gravity triumphed. From their funerals, the first black holes were born. These were not merely remnants, they were seeds. Invisible, silent, and merciless, they pulled their surroundings into order. Gas clouds fell. Stars gathered, galaxies spun into form. From the ashes of those first deaths rose the architecture of the cosmos. Yet the paradox deepens. A black hole consumes, but it also creates. It erases, yet it sculpts. It destroys stars, but may have given galaxies their shape. If the first black hole still lingers, hidden in the deep structure of the universe, then the oldest relic of creation is not a star, not a planet, but a shadow. Can science ever uncover its ashes? Or will the first black hole remain buried forever, a silent witness to the beginning of time itself? For as long as humanity has gazed upward, there has been unease in the stars. To ancient eyes, the night sky was both a map and a mystery. Constellations became myths, and myths became mirrors of human fear. Beasts devouring suns, gods swallowing. The world, abysses from which no return was possible. These were not yet black holes, but they were shadows of the same idea. Intuitions that somewhere beyond sight, the universe contained hungers too great to name. For millennia, astronomy meant charting positions, predicting cycles, mapping the heavens as a clock. The planets obeyed patterns, the moon circled the earth, and the stars wheeled overhead in a silent procession. Aristotle believed that each object had its natural place, the earth at the center, heavy matter falling toward it, the heavens moving in crystalline spheres beyond. The cosmos, he thought, was perfect, eternal, and unchanging. In such a vision, there was no room for collapse. Stars burned perpetually. Matter endured forever. But centuries passed, and the first cracks in that vision appeared. In the 16th century, Copernicus displaced the Earth from the throne of creation, placing the Sun at the center instead. Kepler revealed that planetary orbits were not perfect circles, but ellipses, bound by invisible laws. Galileo, with his telescope, saw mountains on the moon and moons circling Jupiter, shattering the notion of heavenly perfection. Each step drew the universe closer, stripping away divine distance, revealing motion as universal. And then, in the late 17th century, came Newton. With his law of universal gravitation, he unified the fall of an apple with the orbit of the moon. A single equation described the invisible tether binding planets to stars, stars to galaxies. Gravity was revealed not as myth, but as law. Yet even Newton glimpsed deeper possibilities. He imagined a universe where matter, drawn together by gravity, might collapse without end, a vision too strange to embrace, and one that his successors quietly ignored. The first seeds of the black hole concept appeared not with astronomers, but with thinkers who dared to stretch Newton's law to its extreme. In 1783, the English cleric John Mitchell proposed what he called dark stars. If a body were massive enough, he reasoned, its escape velocity would exceed the speed of light. No ray could flee its surface. To distant observers, it would be invisible, hidden, yet immense. Years later, Pierre-Simon Laplace in France independently echoed the idea. Both men imagined cosmic shadows, stars whose gravity had imprisoned even light itself. The mathematics was sound, but the vision was too radical. Without evidence, these dark stars were left as curiosities in the margins of theory. The 19th century brought telescopes powerful enough to map nebulae, revealing that the Milky Way was not alone. Yet still, the notion of collapse was resisted. Stars were thought eternal, fueled perhaps by chemical fire or gravitational contraction. Only in the early 20th century, with the discovery of nuclear fusion, did scientists understand how stars truly burn. But even before fusion was revealed, another revolution had already begun. In 1915, Albert Einstein unveiled his general theory of relativity. Gravity was no longer a force pulling across empty space, but the curvature of space and time itself. Mass bent spacetime, and spacetime guided mass. Planets moved not because of invisible tethers, but because they followed the geometry carved by stars. Suddenly, the universe itself was pliable. Space could bend, twist, and collapse. Time could slow or even end. Einstein's equations were profound, but they carried a hidden prophecy. In 1916, Karl Schwarzschild, a German physicist serving on the Eastern Front during the First World War, found an exact solution to Einstein's field equations. It described a point of infinite density, what we now call a singularity, surrounded by a surface beyond which nothing, not even light, could escape. This boundary became known as the event horizon. Schwarzschild had mathematically described a black hole, though the term itself would not be coined until decades later. Einstein himself rejected the idea. He saw these solutions as mathematical artifacts, not physical realities. To him, nature would never permit such absurdities. Singularities seemed to signal a failure of theory, not a window into truth. For years, most physicists agreed. Black holes were dismissed as curiosities, logical phantoms haunting the equations of relativity. But the cosmos was less forgiving. In the 1930s, Subramanian Chandrasekhar calculated the limits of stellar stability. He showed that stars above a certain mass could not resist their own gravity once nuclear fuel was spent. White dwarfs and neutron stars could exist, but beyond a threshold, collapse was inevitable. Stars more than about 3 times the Sun's mass would implode into something beyond known physics. This idea was fiercely resisted, most famously by Arthur Eddington, who believed nature would find a way to prevent such catastrophes. But time proved Chandrasekhar right. Then came the 1960s. Radio telescopes, tuned to the sky's invisible frequencies, discovered quasars, objects so luminous they outshone entire galaxies. Their light, shifted far into the red, came from billions of light years away, meaning they were ancient, among the first structures formed. The only engines powerful enough to fuel them were black holes, swallowing matter at ferocious rates, converting infall into radiation. What had been dismissed as fantasy now announced itself with blinding clarity. Closer to home, X-ray astronomy revealed strange companions to ordinary stars. One of them, Cygnus X1, emitted powerful X-rays from a region where no visible star could be seen. Its mass, calculated from the motion of its companion, was too great for any known stellar remnant. It was, by every measure, a black hole. The term itself, popularized by John Wheeler in 1967, soon entered both science and imagination. By the end of the 20th century, black holes had shifted from speculation to certainty. They were no longer exotic exceptions, but central to cosmic architecture. At the hearts of galaxies, including our own, supermassive black holes, millions or billions of times the sun's mass reigned. Around them, stars orbited like moths around invisible flames. From them, jets of plasma extended for hundreds of thousands of light years, sculpting entire galaxies. Yet with every discovery, a deeper question emerged. If supermassive black holes existed less than 1 billion years after the Big Bang, they must have grown from seeds, smaller black holes, born from the first stars, or perhaps from processes even more ancient. Were these seeds the ashes of the first black holes? If so, they are not only relics of collapse, but ancestors of structure itself. Modern astronomy looks backward in time, peering through cosmic history. The farther we see, the younger the universe appears. The Hubble Space Telescope revealed galaxies forming when the cosmos was still in its youth. The James Webb Space Telescope has pushed further, glimpsing light from stars and galaxies born just a few 100 million years after the Big Bang, and yet, even Webb cannot see the very first black hole. Its ashes are buried deeper still, hidden. In the infancy of time, the journey to uncover them begins not with light, but with shadow. Astronomers now turn to indirect traces, gravitational waves rippling through spacetime, chemical fingerprints in ancient stars, distortions in the cosmic microwave background. Each clue whispers of collapse, of gravity's triumph, of a darkness older than galaxies themselves. The story of black holes began with myths of devouring beasts and equations scribbled in war. But behind both myth and mathematics lies a deeper truth the universe may carry within its scars from its very birth. Scars that take the shape of black holes, scars that may never heal, but instead grow, merge, and sculpt. The ashes of the first black hole are not marked by stone or fire. They are invisible, intangible, yet everywhere. The galaxies we see today may be monuments raised upon their silent foundations. And so the search continues, not only for black holes in the present, but for the first one of all. From the moment the idea of black holes moved from mathematics to observation, science entered a territory that felt less like physics and more like myth. Here was a phenomenon that defied ordinary categories, a place where equations ended, where certainty dissolved. The shock was not that black holes might exist, but that they must exist, demanded by the laws of nature themselves. Gravity, the most familiar of forces, was revealed to have no limit. The same invisible pull that guides a falling apple, that steers the moon in its orbit, if left unchecked, could collapse matter without end. Einstein's equations made this clear. Mass bends spacetime, and when enough mass accumulates, the bending becomes infinite. At that point, time itself falls inward, and space closes upon itself. A singularity forms a point of infinite density, confined within zero-volume dot. To the human imagination, infinity is less a number than an abyss. How could the universe allow such contradictions to exist within itself? Physics is built upon measurement, and yet a singularity permits no measurement, no description, no boundary condition. It is a wound in space-time, a tear where the fabric of law gives way to the unknown, and surrounding this wound is the most haunting feature of all, the event horizon. A boundary not of matter, but of fate. Cross it, and escape becomes impossible. Not for ships or signals, not even for light itself. The event horizon is not a surface one can touch, but a limit of return, the ultimate horizon of knowledge. For the first time in science, a boundary appeared that was not physical, but ontological, a region where reality itself could not be witnessed. This revelation shook physics to its foundations. For centuries, nature was thought to be transparent, to reason. But black holes are opaque, not only to light, but to law. They do not merely hide what lies within, they deny access altogether. The shock deepened in the mid-20th century, when evidence revealed that black holes were not rare oddities, but common engines of the universe. Quasars, blazing brighter than galaxies, were fueled by black holes feeding upon matter. Entire galaxies appeared structured by their central singularities. Jets of radiation extended across intergalactic space, powered by rotational energy extracted from these cosmic abysses. What was once dismissed as theoretical fantasy had become the machinery of the cosmos. But the most startling discovery was temporal. Quasars were seen at great distances, their light traveling to Earth across billions of years. The farther away they were, the younger the universe was when their light began. Astronomers realized that supermassive black holes, millions or even billions of solar masses, already existed less than 1 billion years after the Big Bang. By cosmic standards, this was almost immediate. The question struck like thunder. How could black holes so immense form so quickly? Stars collapsing into stellar mass. Black holes provide seeds, yes, but their growth requires time, limited by the rate at which matter can fall inward without blasting itself away in radiation. Yet quasars show that these objects grew far faster than models permit. The implication was unsettling. The universe's earliest epochs may have been shaped not by stars alone, but by black holes born under conditions still unknown. The paradox widened when black holes were placed under the gaze of quantum theory. According to Einstein's relativity, once matter passes the horizon, it is lost forever. Information is erased, crushed into the singularity. But quantum mechanics forbids such erasure. In the quantum world, information is indestructible. It may be scrambled, dispersed, hidden, but never lost. Thus was born the black hole information paradox, two of physics' greatest theories, relativity and quantum mechanics, indirect contradiction. Stephen Hawking sharpened the dilemma in 1974. He showed that black holes are not entirely black. Through quantum effects at the event horizon, they emit faint radiation, now known as Hawking radiation. This implies that black holes slowly evaporate, releasing energy until, in inconceivable spans of time, they vanish. Yet what becomes of the information that fell inside? Does it evaporate too, breaking the rules of quantum theory? Or does it linger, encoded somehow, upon the horizon itself, as some physicists suggest? Here, the scientific shock turned philosophical. If information can truly be destroyed, then predictability in physics collapses. The universe ceases to be lawful in the deepest sense. The arrow of cause and effect would fray, and science itself would lose its foundation. Black holes, born from the simplest equation of gravity, had become paradox machines, challenging not only what exists, but what can ever be known. The shock extended to cosmology as well, for if black holes existed at the dawn of galaxies, they may have shaped the entire architecture of the cosmos. Without them, galaxies might not form as they do. Stars might not cluster. Planets and life itself might never arise. Black holes, once imagined as destroyers, revealed themselves as architects. And if supermassive black holes had already grown in the universe's youth, perhaps their seeds were even older. Perhaps some were born not from stars, but from the fabric of the universe itself, in its first chaotic moments. This raised an even darker possibility. Primordial black holes. In the first fractions of a second after the Big Bang, density fluctuations may have collapsed regions of spacetime into black holes, bypassing stars entirely. If so, the first black holes predate light, predate galaxies, predate even atoms. They may still roam the universe today, invisible but immense. Some could be small, evaporating through Hawking radiation. Others could be massive, hiding as dark matter, shaping cosmic evolution unseen. The implications are staggering. If primordial black holes exist, then the ashes of the first black hole are not scattered far in cosmic history. They are here, woven into the present. They may drift in the halos of galaxies, or even pass silently through the solar system. The universe could be seeded, haunted, and scaffolded by black holes that have existed since its birth. But the most unsettling shock remains conceptual. In every other domain of science, understanding deepens as one descends into detail. Molecules to atoms, atoms to nuclei, nuclei to quarks. Each step yields clarity. Black holes reverse this pattern. The closer one approaches, the less the laws apply. At the singularity, description ends altogether. To confront a black hole is to confront the limit of science itself. And yet, black holes are not distant curiosities. The supermassive black hole at the center of our galaxy, Sagittarius Asterisk, binds hundreds of billions of stars, including the Sun. Without it, the Milky Way might never have taken its form. Around us, stars orbit silently under its sway. We live, not beside a paradox, but within one. Thus the shock is double. Black holes are both everyday and impossible. They are indispensable to the universe's structure, yet intolerable to its laws. They are creators and destroyers, predictable in their gravity yet paradoxical in their physics. In their presence, human understanding oscillates between awe and fear, as though standing on the shore of an ocean whose depths contain not only storms but contradictions, from the first predictions of Mitchell and Laplace to Schwarzschild's wartime solution to the blazing quasars revealed by radio telescopes. The scientific shock of black holes has never subsided. Each discovery resolves one mystery only to open a deeper one. Each glimpse reveals that the first black holes were not merely remnants of stars, but perhaps the universe's own fossils, its most ancient memory preserved in silence. And so the question remains, what were the ashes of the very first black hole? Were they the remains of a collapsed giant star, long vanished in the darkness of the early cosmos? Or were they born primordial, older than stars themselves, a relic from the instant of creation? The shock is not only that such questions can be asked, but that they must be. The very existence of black holes demands them. As the 20th century matured, science no longer asked whether black holes might exist. The question had shifted into one far more ambitious. Where are they, and what role did they play in shaping the universe itself? To pursue that trail, astronomers and physicists began probing deeper with telescopes, with satellites, with instruments buried in ice and stone. each designed to reveal what the naked eye and even the imagination could not. The first target was starlight itself. In the 1960s and 1970s, Vera Rubin mapped the rotation of spiral galaxies. What she found was a pattern that defied Newton's laws if only visible matter was present. Stars, far from the galactic center, moved far too quickly to be held by the gravity of luminous matter alone. The missing mass implied the presence of something invisible, something dark. Though her work illuminated the problem of dark matter, it also raised an adjacent suspicion. Perhaps black holes were not only singularities within galaxies, but essential to their very birth. Their gravity might have shaped the unseen scaffolding on which galaxies rest. Attention then turned to the most violent sources of radiation in the cosmos. Quasars, discovered through radio astronomy, glowed with the brilliance of 1 trillion stars, yet from regions no larger than our solar system. The only engines capable of such power were supermassive black holes consuming gas at ferocious rates. By tracing quasars to extraordinary distances, astronomers peered into the early universe and found that such engines already blazed. Less than 1 billion years after the Big Bang, this was no longer simply evidence of black holes. It was a timeline problem. Seeds must have formed earlier than expected, raising the possibility that the very first black holes were direct children of the first stars, or perhaps older still, born from the density chaos of the Big Bang itself. To refine these questions, scientists turned to simulation. On supercomputers, they recreated the gravitational collapse of primordial gas clouds under the cold shadow of dark matter halos. In these simulations, the first stars, population 3 stars, emerged. These giants, tens to hundreds of times more massive than the Sun, lived brief and violent lives. Within only a few million years, they exploded as supernova, seeding space with heavy elements. Some collapsed directly into black holes of dozens, perhaps hundreds, of solar masses. These were the first candidates for the seeds of cosmic structure, but simulations hinted at another, more radical path. Not all primordial clouds fragmented into stars. Some, under particular conditions, collapsed directly under their own gravity, bypassing fusion, bypassing starlight. These direct collapse black holes could form with masses of 100,000 suns or more, explaining the existence of quasars at impossible distances. If such collapses occurred, the first black holes were not ashes of stars at all, but entities born from the raw gas of creation itself. Black holes without funerals, born without light. Evidence was sought in chemical fossils, the oldest stars in the Milky Way halo. These ancient survivors are relics of the early cosmos, their compositions frozen since their birth. Some display unusual chemical signatures, rich in elements like carbon and magnesium, yet poor in iron. Such fingerprints suggest they were born from gas enriched by peculiar supernova, perhaps the explosions of population 3 stars. And if some of those giants ended not as explosions, but as collapses, their remains might still linger today as black holes drifting unseen. The search expanded to the very fabric of the universe's oldest light, the cosmic microwave background. This afterglow of the Big Bang, mapped in exquisite detail by satellites such as WMAP and Planck, contains subtle fluctuations, ripples of density from the infant cosmos. Primordial black holes, if they formed in abundance, would have left imprints upon this light. The absence of certain signatures constrained their possible sizes, but did not erase the possibility. Some windows remained open. Black holes of asteroid mass, of stellar mass, of tens of thousands of suns, could still be hiding. Unseen yet influential, another line of inquiry emerged in 2015, when the Laser Interferometer Gravitational Wave Observatory LIGO recorded the faint tremor of spacetime itself. Two black holes had merged over 1 billion light-years away, releasing more energy in a second than all the stars in the universe combined, yet not as light, but as ripples in the fabric of reality. What shocked physicists was the mass of the merging pair, about 30 times the mass of the Sun each. Stellar evolution models predicted fewer black holes of that size, especially in pairs. Some speculated they might be primordial, relics from the early universe now colliding in darkness. Gravitational waves opened a new kind of telescope, one that does not see light, but listens to spacetime. With each detection, science gains a new clue about the black hole population, their sizes, their spins, their frequencies. Already, dozens of mergers have been recorded. Some fall neatly into expectations. Others stretch them, hinting at origins older and stranger than ordinary. Stellar collapse. In time, these signals may reveal whether the ashes of the first black holes echo in spacetime itself. Meanwhile, observations of galaxy clusters provided further mysteries. The Bullet Cluster, a collision of two massive clusters of galaxies, revealed a striking separation. X-rays traced hot gas slowed by collision, while gravitational lensing, the bending of background light by mass, revealed dark matter passing through, barely interacting. Within these distributions, some models allow for populations of primordial black holes mixed invisibly with dark matter. If so, then the ashes of the first black hole are not lost. They are written invisibly into the scaffolding of the cosmic web. Cosmic simulations, such as the Millennium Simulation and Illustris, have revealed how galaxies form and cluster, tracing the filaments of dark matter as a skeleton of cosmic architecture. In these models, black holes are not passive passengers but active architects, regulating star formation through their feedback. Without them, galaxies grow too large, too luminous. With them, balance is restored. The implication is profound. Black holes were not latecomers, but central players. They may have been among the earliest structures to form, seeding the order of the universe we see today. The deeper the investigation reached, the more questions surfaced. Were the first black holes born from collapsing stars, or did some emerge in the first second of cosmic time? Are they scattered like dust across the universe, tiny and evaporating, or concentrated in the hearts of galaxies, colossal and enduring? Have some already vanished through Hawking evaporation, leaving behind only a whisper of radiation? Or do they remain hidden in halos, masquerading as dark matter itself? What became clear is that the search for the ashes of the first black hole is not confined to one corner of physics. It stretches across disciplines. Astrophysicists trace galaxies and quasars. Cosmologists map the microwave background. Particle physicists hunt for exotic candidates that might link dark matter to black holes. Gravitational wave astronomers listen for the deep chords of ancient mergers. Each frontier approaches the same question from a different path, yet all converge on the same abyss. The investigation is not merely technical, but existential. To trace the first black hole is to trace the memory of the universe itself. It means asking whether creation began with collapse, whether darkness was not an afterthought but an origin. For in the ashes of the first black hole lies a truth both humbling and haunting, that the most invisible structures may be the most enduring. That destruction may be the deepest kind of creation. The search continues, not because answers are near, but because the questions refuse to fade. Every new observation sharpens the paradox. Black holes are common, yet their origin remains uncertain. They are central, yet elusive. The deeper science peers, the more it finds not clarity but mystery, the kind of mystery that binds inquiry, itself pulling thought as gravity pulls stars into depths that cannot let go. The deeper science probed into the early universe, the more unsettling the mystery became. What began as a search for black holes in distant galaxies turned into a confrontation with impossibility itself. Observations from the James Webb Space Telescope brought this paradox into sharp relief when its infrared eyes opened upon the cosmos. It revealed galaxies shimmering at red shifts beyond 7, galaxies that existed when the universe was less than 800 million years old. At their centers lurked quasars powered by black holes of hundreds of millions, even billions, of solar masses by every conventional model. Such behemoths should not exist so soon. The growth of black holes, through the steady accretion of matter, and the occasional merger, is not quick enough to reach such colossal scales in so little time. Something had accelerated their formation. Something was wrong with the timeline. If the universe had barely finished forming its first stars, how could it already host engines of such ferocious power? This is where speculation turns darker. One possibility is that the first stars themselves, massive and short-lived, collapsed into black holes, far larger than ordinary stellar remnants, hundreds of times the mass of the Sun. These giants, when fed by streams of primordial gas, could have swelled quickly into the seeds of quasars. Another possibility is even more radical, that some clouds of hydrogen and helium never ignited as stars at all, but collapsed directly into black holes of 100,000 suns or more. These direct collapse black holes could have bypassed stellar evolution entirely, forming vast gravitational wells in the earliest epochs, and yet, deeper still lies a possibility more profound. Some physicists argue that black holes might have been born not after stars, but before them, formed from density fluctuations in the first second after the Big Bang. These primordial black holes would not be ashes of starlight, but relics of cosmic birth itself, fossils older than galaxies, older than light. If such objects survived, they could still drift unseen through the cosmos, their gravity influencing galaxies, their presence masquerading as dark matter. The unease grows sharper with each discovery. Quasars in the infant universe are not rare. Exceptions, they appear with alarming regularity. Each one is a reminder that our models of cosmic evolution may be incomplete. Perhaps gravity worked differently in the early universe. Perhaps the laws of physics we know are only approximations, valid for the present but not the past. The information paradox deepens the tension. According to classical general relativity, information that falls into a black hole is lost forever. Yet quantum mechanics insists that information cannot be destroyed. This clash between two pillars of modern physics creates a paradox at the heart of black hole theory. If the first black holes still exist, do they still carry within them the encrypted memory of the universe's beginnings? Or has that information dissolved into nothingness, breaking the most sacred law of physics? The mystery expands further when considering the role of black holes in shaping structure. Simulations show that galaxies form along filaments of dark matter, yet the brightest quasars appear at the densest nodes of this web. Black holes are not only passengers but participants, guiding gas, igniting starbursts, and regulating cosmic architecture, the possibility emerges that the ashes of the first black holes are not scattered randomly, but woven into the cosmic web itself, silently shaping every star, every galaxy, and still, contradictions multiply. Some models predict that black holes should take billions of years to grow into supermassive giants, yet we see them already present in the first billion. Others predict that small black holes from population 3 stars should be abundant, yet they remain elusive. Gravitational wave observatories detect mergers of black holes with masses that puzzle stellar evolution, raising suspicions of ancient, primordial origins. The evidence refuses to align, pointing instead toward something deeper, stranger, more difficult. Philosophical unease takes root. If black holes can form before stars, before galaxies, before light, then they are scars written into the universe itself. They would represent collapse without creation, voids older than order. In such a vision, the first black hole is not a remnant of starlight, but a coiled knot of spacetime from the very instant of birth. The universe would not only have been seeded with matter and energy, but scarred with wounds that never healed. The paradox sharpens when considering evaporation. Hawking radiation predicts that black holes lose mass over time, evaporating across unimaginable epochs. The smallest black holes, born in the early universe, might already have vanished, leaving behind a whisper of radiation. The ashes of the first black holes carried not in matter, but in faint cold photons. If true, the evidence of their existence is already gone, dissolved into the background of the cosmos, undetectable to present eyes. Yet if larger primordial black holes still survive, they might explain the mystery of dark matter, the invisible mass that sculpts galaxies and holds them together. Each possibility adds to the unease. If dark matter is made of black holes, then the universe is scaffolded not by exotic particles, but by ancient graves of collapsed space. Every galaxy would orbit an unseen cemetery, its structure defined by the ashes of the first black holes. Meanwhile, observations of the Hubble constant, the rate at which the universe expands, deepen the tension. Different methods yield different results, a discrepancy known as the Hubble tension. Some physicists speculate that unknown physics in the early universe may be to blame, perhaps linked to black holes themselves. If so, then the ashes of the first black holes are not simply remnants of history, but active agents in shaping cosmic evolution. The mystery, then, is no longer confined to astrophysics. It reaches into cosmology, particle physics, and even philosophy. The first black holes blur the line between beginning and end, between matter and void. They raise questions about the nature of time itself. If collapse and creation are intertwined, perhaps the universe is not linear but cyclical, each epoch seeded by the death of the last. Penrose's conformal cyclic cosmology dares to suggest that the evaporation of black holes could seed future universes. In such a picture, the ashes of the first black hole may not only shape this cosmos, but ignite the next. And so, the mystery deepens into unease. The closer science looks, the earlier black holes appear. The more telescopes observe, the more contradictions emerge. Instead of answers, discoveries multiply paradoxes. The first black hole may have been stellar or primordial, or neither. Its ashes may linger in radiation, in dark matter, or in the very shape of the cosmic web. What becomes clear is that this is not a story of certainty, but of tension. Science stands at the edge of comprehension, staring into the abyss. Each discovery acts not as resolution, but as escalation, pulling thought deeper into paradox. The ashes of the first black hole are not only a question of astrophysics, but of existence itself. How creation begins, how time remembers, and whether collapse is not an end but the oldest form of birth. The search presses forward, yet the mystery grows. The first black hole hides not only in the fabric of space, but in the contradictions of thought. Its ashes scatter across galaxies, across simulations, across paradoxes. In seeking it, science does not find resolution, but confrontation. With the limits of knowledge, the mystery deepens, and the abyss gazes back. The ashes of the first black hole are not found in telescopes alone. They live in theories, in fragile models stretched to the breaking point. To confront their origin, science must imagine realities stranger than the cosmos already revealed. The first great speculation belongs to primordial black holes. Unlike those born from collapsing stars, primordial black holes would have emerged seconds after the Big Bang, when the universe was a dense, turbulent sea of plasma. In those first instants, matter was unevenly distributed. Where density was slightly higher, gravity could have overwhelmed expansion, crushing regions into black holes before atoms or stars ever existed. Their masses might range from tiny specks smaller than mountains to objects rivaling thousands of suns. Some would have evaporated by now, releasing Hawking radiation in their final sigh. Others, heavier and more enduring, might still drift invisibly, shaping galaxies, masquerading as dark matter. If true, the first black hole was not a grave of starlight, but a scar from creation itself, a shadow born before light. Another path leads to the direct collapse model. Instead of stars forming and then dying, immense primordial gas clouds could have collapsed under their own gravity directly into black holes. Without metals to cool them, without turbulence to fragment them, these clouds could have skipped stellar ignition. The result: black holes with masses of 100,000 suns or more, born whole from the universe's infancy. These giants could explain the rapid appearance of quasars less than 1 billion years after the Big Bang, the first black hole. In this vision was not the end of a star, but the beginning of a galaxy. Speculation stretches further with Hawking's radiation. In 1974, Stephen Hawking proposed that black holes are not entirely black. Quantum fluctuations near the event horizon allow particles to escape, slowly draining the hole's mass. Over unimaginable timescales, black holes evaporate. If primordial black holes were tiny, they may already have dissolved, their ashes scattered, as faint gamma-ray whispers across the universe. Detecting such radiation would not only confirm their existence, but reveal that the first black holes lived and died long before galaxies took shape. Yet none has yet been found. Then comes the information paradox. If information falls into a black hole, does it vanish forever? Classical relativity suggests yes. Quantum theory demands no. The contradiction forces new speculation. Perhaps black holes are not voids, but vaults, storing information on their horizons in microscopic patterns. The holographic principle, born from this paradox, suggests that everything inside a black hole is encoded on its surface, a universe written on a boundary. If true, the first black hole may still carry within its horizon the encoded memory of the early cosmos. It would not only be an object but an archive, a library of creation's earliest chapters. Some theories go further still. In loop quantum cosmology, space-time itself is quantized. Singularities, like those predicted in black holes, are replaced with finite structures. Collapse does not reach infinite density but bounces, transforming contraction into expansion. In this vision, black holes might be gateways to new universes. The first black hole could have ignited not just galaxies, but entirely separate realms of existence, each bounce birthing a cosmos beyond observation. String theory extends the speculation to higher dimensions. Gravity, unlike the other forces, may leak into extra dimensions, creating effects that mimic unseen matter. Black holes, in this framework, might resonate across dimensions, their formation and evaporation tied to structures beyond perception. The first black hole, then, could be not only primordial but extra-dimensional, its ashes scattered into realities that shadow our own. Some suggest that black holes themselves might constitute dark matter. If a population of primordial black holes survived from the earliest seconds, they could account for the invisible mass sculpting galaxies. This theory, long dismissed, has revived as gravitational wave observatories reveal mergers of unexpectedly massive black holes. Their origin may lie not in stars, but in the deep past, echoing across billions of years. If this is true, then every galaxy is scaffolded by black holes, every orbit defined by ancient graves of collapsed space. A more radical speculation comes from entropic gravity, the idea that gravity itself is not fundamental but emergent, arising from the statistical behavior of microscopic information. In this vision, black holes are not exotic monsters but natural consequences of information flow. Their horizons are thermodynamic surfaces, their mass a measure of entropy. If this model is true, the ashes of the first black hole are not matter at all but patterns of information, echoes of entropy written into spacetime. The most daring speculations unite cosmology with philosophy. Roger Penrose's conformal cyclic cosmology suggests that universes repeat in endless succession. In each eon, black holes evaporate until only radiation remains. At that moment, scale ceases to matter, and a new Big Bang ignites. In this model, the ashes of the first black hole are not relics, but seeds, carrying memory from a previous universe into ours. The very first black hole may not belong to this cosmos at all, but to one that ended billions of years before it began. Even more speculative is the notion that black holes might serve as gateways, wormholes or bridges to parallel universes. In some models, the collapse of matter does not end in singularity but tunnels through spacetime, opening into another region. The first black hole, in this daring imagination, was not only a tomb but a doorway. Its ashes would not rest in our universe but in another, unreachable but real, and yet each theory remains fragile. Primordial black holes have left no decisive trace. Direct collapse models require conditions that may be rarer than imagined. Hawking radiation has never been directly observed. The holographic principle remains an elegant conjecture. Loop quantum. Cosmology and string theory still lack empirical proof. Penrose's cyclic eons remain visions untested. Still, speculation is not wasted. Each theory reveals the depth of the mystery, the limits of current knowledge. To seek the ashes of the first black hole is to confront the boundaries of science itself. Are black holes engines of galaxies, fossils of creation, seeds of future universes, or bridges to unseen dimensions? Or are they all of these at once, their reality transcending our categories? The paradox is haunting. Black holes erase matter, yet science imagines them as creators. They destroy information, yet inspire theories of memory. They end stars, yet may seed universes. If the first black hole was primordial, then destruction and creation were entwined from the first moment, collapse inseparable from birth. The ashes of the first black hole are not only cosmic but philosophical, challenging every notion of time, of memory, of beginning. And so the story of the first black hole is not written in certainty, but in speculation. Primordial collapse, direct collapse, evaporation, holography, cycles, dimensions. Each vision is a fragment, a reflection cast on the abyss. Together they reveal that the search is not only for an object, but for understanding itself. The ashes of the first black hole are the ashes of certainty, leaving only mystery glowing in their wake. The search for the ashes of the first black hole is not a journey through myth alone. It is a pursuit waged with instruments stretched to the limits of human ingenuity. If the first black hole still echoes through the universe, its presence may be revealed not in sight, but in patterns, distortions, or faint signals carved into the fabric of spacetime. To glimpse it, science must reach farther than ever before. The first tool lies in the James Webb Space Telescope, suspended 1 million miles from Earth, cooled to near absolute zero. Its golden mirrors stare into the ancient darkness. With infrared eyes, it looks back over 13 billion years, probing the first galaxies. Already it has revealed quasars blazing at redshifts higher than expected, their engines powered by black holes that seem impossibly massive for such an early epoch. These findings intensify the puzzle. Did these giants grow from the remnants of the first stars, or were they born far earlier, from direct collapse or even primordial origins? Webb cannot see the first black hole directly, but it sketches its fingerprints, galaxies to luminous, quasars to ancient structures, to vast to exist so soon. On the ground, the extremely large telescope, ILTI, rises from the deserts of Chile. With a mirror spanning nearly 40 meters, it will collect light with a precision unmatched by any instrument before it. Alongside it, the 30-meter telescope, TMT, and the giant Magellan telescope, GMT, will map faint galaxies, measure their motions, and weigh the invisible engines at their cores. Their purpose is simple: to catch black holes in the act of forming, to identify the first seeds around which galaxies crystallized. But not all evidence comes from light. The universe whispers in gravitational waves, ripples in space-time born when black holes collide. Since 2015, LIGO and Virgo have detected dozens of such mergers. Some involve black holes with masses that do not fit neatly into stellar evolution, suggesting ancient origins. Future instruments, like ELIS, the Laser Interferometer Space antenna, will drift through space, listening to lower frequency waves. It will detect the merging of supermassive black holes, tracing their growth across cosmic history. If a primordial black hole once seeded a quasar, LISA may hear its descendants merging in the darkness. The cosmic microwave background also serves as a silent witness. This relic radiation, frozen from when the universe was 380,000 years old, carries the imprints of early structures. If primordial black holes existed, their gravitational influence could have distorted this radiation. Missions such as Planck and future polarization surveys search for these subtle scars. Anomalies in the temperature fluctuations, unexplained cold spots, alignments or distortions may yet reveal the ashes of the first collapse. Gravitational lensing provides another tool. When light from distant galaxies bends around invisible mass, it sketches the presence of what cannot be seen. The Euclid mission, launched by the European Space Agency, and the Vera Rubin Observatory on Earth will chart these distortions across billions of galaxies. If dark matter halos hide populations of primordial black holes, lensing may expose them. A sudden brightening, a flicker of distortion in a background star, could betray the silent passage of a black hole no larger than a mountain but as heavy as the moon. Meanwhile, beneath Earth's surface, in caverns shielded from cosmic rays, detectors lie in silence. Instruments like Xenant, Lux-Zeppelin, and Pandex wait for faint interactions between dark matter particles and xenon atoms. While these detectors primarily hunt for WIMPs, weakly interacting massive particles, they also constrain the role of black holes. If no dark matter particles appear, then primordial black holes gain plausibility as the hidden scaffold of the cosmos. In this way, absence itself becomes evidence. The ashes of the first black hole may also be revealed in high-energy skies. Athena, the European Space Agency's planned X-ray observatory, and NASA's LINX concept will probe the hot gas surrounding black holes. By tracing X-ray emissions from the earliest galaxies, they aim to catch black holes feeding, swallowing matter, and igniting quasars. If black holes appeared earlier than expected, these instruments will see the echoes of their feasts. Cosmic surveys add yet another layer. The Nancy Grace Roman Space Telescope will map vast regions of sky with exquisite precision. Its wide field lensing surveys will complement Euclid, searching for distortions caused by invisible structures. Together, these observatories will build a three-dimensional map of cosmic matter, illuminating where gravity outweighs starlight. Hidden within that scaffolding may lie the ancient bones of the first black holes, and still, science turns to theory as much as observation. Particle physicists probe the Higgs field, testing whether the vacuum itself is stable. If unstable, the universe could collapse into a lower energy state, triggering new births of black holes. Others modeled the collapse of primordial gas with supercomputers, watching as filaments of dark matter and hydrogen weave galaxies around gravitational seeds. These simulations hint that without black holes, the universe would lack the order we see today. The ashes of the first may be not a relic, but the very foundation of structure. Gravitational wave astronomy may soon reach even deeper. As detectors grow more sensitive, they may capture waves from black holes formed not in stars, but in the first seconds after the Big Bang. Such a detection would confirm primordial origins. It would mean the first black hole predates the first atom. Even the 21-centimeter line of hydrogen, emitted when electrons flipped spins in the early universe, may carry clues. Radio telescopes, such as LOFAR and the coming square-kilometer array, aim to map this signal across cosmic dawn. If black holes heated hydrogen gas, their fingerprints may appear as shadows or distortions in the radio glow of the early cosmos. Yet each tool faces limits. Webb can see galaxies, but not isolated black holes. LIGO can hear mergers, but not the silent drift of solitary giants. CMB maps reveal scars, but not the culprits that made them. Direct detection experiments may never find a signal, forcing reconsideration of what dark matter is. The search stretches science toward its horizon, chasing something that may never be directly seen. Still, the pursuit endures. For to find the ashes of the first black hole is to answer more than one question. It is to know whether destruction and creation are twins, whether the universe began with collapse as much as with expansion, whether the gravity that binds galaxies is woven from ancient graves of space itself. In deserts and mountains, in orbit and in silence underground, humanity builds its tools. Telescopes stretch mirrors to catch the faintest photons. Interferometers measure ripples smaller than atoms. Detectors sit in quiet, hoping for the gentlest touch of a hidden particle. Each is a lantern in the dark, searching for the invisible tower that holds the cosmos together. Perhaps the ashes of the first black hole will never be seen directly. Perhaps they will only ever be inferred, glimpsed as distortions, echoes, or whispers. Yet even that would be enough. To trace their existence is to know that the universe remembers its earliest scars, carrying them forward across billions of years. The scientific pursuit is relentless because the mystery demands it. To find the first black hole is to approach the moment when gravity first sank its claws into creation, when silence turned to collapse, when darkness became more enduring than light. And so the search continues, with every tool humanity can build, chasing an object that may be eternal or may already be gone. A search not only for an object, but for the origin of structure, the seed of galaxies, the shadow that shaped everything. The ashes of the first black hole may be hidden, but science will not stop reaching into the dark. In the beginning, there was silence. Before galaxies stretched their arms across the void, before the first stars ignited, there was only a dark sea of hydrogen and helium, drifting without form. And then gravity began to gather, fire lit, and the first suns were born. They burned furiously, brilliant but brief, and when their cores collapsed, they left behind something stranger than fire. They left behind the first black holes, graves of stars that became architects of the future. To imagine the ashes of the first black hole is to imagine time itself carrying memory. For in those ancient deaths, matter was erased, but gravity remained. Those early collapses pulled at their surroundings, guiding gas into galaxies, seeding the first quasars, setting in motion the architecture of everything that followed. In this sense, the first black hole was not only an end, it was a beginning. Every galaxy seen today carries this legacy. At their centers lie supermassive black holes, millions or billions of times the mass of the Sun. They shape the spin of stars, regulate the growth of galaxies, and flare as quasars visible across the universe. These giants are the descendants of the first collapse, the silent lineage of an ancient darkness. To look into the night sky is to see their fingerprints everywhere, and yet black holes are more than engines. They are paradoxes. They erase information, swallowing matter beyond recall, and yet quantum theory insists that information cannot be destroyed. The universe cannot forget. Somewhere in the mathematics lies an answer not yet revealed, whether the ashes of the first black hole still hold the memory of the universe's birth, or whether they have been smoothed into silence by time itself. For humans, the weight of this is more than abstract. Every atom in the body was forged in stars, but the galaxies that gave rise to those stars were shaped by black holes. Life itself, fragile and fleeting, rests on foundations sculpted by destruction. To live is to inherit both starlight and shadow. The image becomes haunting, a cosmos built not on permanence, but on collapse. The first black hole did not preserve what it devoured. It did not shine. It became absence. And yet absence had gravity, and gravity shaped creation. In this way, the ashes of the first black hole are not a ruin, but a blueprint, invisible but essential. There is a lesson in this paradox. The universe reminds us that loss does not erase meaning. The collapse of a star gave rise to galaxies. The erasure of matter created structure. Even destruction becomes a foundation for life. In the silence of the first collapse lies the resonance of every future world. Philosophers have long pondered whether history repeats, whether time circles endlessly. Some see black holes as symbols of recurrence, matter drawn in, erased, and reborn. Others see them as symbols of finality, places where endings are absolute. Yet the truth may lie somewhere deeper. A black hole is both an end and a beginning, a door that locks behind us but opens into something unseen. The ashes of the first black hole may still burn invisibly, shaping the expansion of the universe in ways we cannot yet perceive. As science probes deeper, the mystery only sharpens. Observations push closer to the dawn, revealing galaxies too early, black holes too massive, structures too intricate, models strain, theories falter. The closer we look at the universe's beginning, the more it recedes into paradox. Perhaps this is the universe's way of reminding us that not all truths yield to equations. Some are woven into the fabric of existence, meant to be lived rather than solved. And yet the pursuit continues. Instruments are built to listen for whispers, to catch shadows, to map distortions in the dark. In deserts, in orbit, beneath mountains, humanity builds its lighthouses, not of stone, but of mirrors and detectors. Each one points into the void, asking the same question: what remains of the first collapse? What lingers of the first black hole? Whether or not science finds a definitive answer may be beside the point. The search itself transforms our understanding. To seek the ashes of the first black hole is to recognize that the universe is not only a place of light, but also of silence. That creation emerges from endings. That life itself is entangled with collapse. In this reflection lies something deeply human. Every life, like every star, ends. Every memory fades. But endings are not voids. They are transitions, leaving behind echoes, foundations, and gravity for what follows. The first black hole may be gone, evaporated through Hawking radiation or lost in mergers, but its ashes remain in the galaxies that spin today, in the stars that light the night, in the atoms that breathe as humanity. Perhaps the first black hole still exists, drifting unseen in some corner of the cosmos. Or perhaps it has long since dissolved into radiation, its ashes spread across the background glow of the universe. Either way, its legacy endures. Its presence is not measured in its survival, but in its influence. Creation itself bears its fingerprint. The night sky then becomes a graveyard and a cathedral at once. Every shining star is a hymn to starlight. Every spiral galaxy is a monument to collapse. And every shadow, every unseen mass, may be the ashes of the first black hole, still shaping the dance of time in the end. Perhaps this is the greatest lesson, that the universe does not divide neatly into beginnings and endings. They are the same act seen from different sides. A star dies, and a black hole is born. A black hole erases, and a galaxy emerges. The ashes of the first collapse are not an afterthought. They are the foundation of everything. And so the story closes not with an answer, but with a meditation. Humanity lives in a cosmos sculpted by forces it cannot see, guided by structures it does not yet understand. To search for the ashes of the first black hole is to search for the memory of the universe itself. It is to ask whether creation can exist without destruction, whether life can exist without death, whether meaning can exist without silence. The final image is quiet. The universe expanding, galaxies spinning, stars burning, and beneath it all, an invisible architecture, ancient and enduring. The ashes of the first black hole lie there, unseen, holding the cosmos together, and in that silence, the haunting question remains: if creation is born of collapse, then is every beginning already an ending, and every ending already a beginning?